soil cement road pavement. Translation provided on behalf of higher educational institutions with the support of the company National Resources. South Australia. A network of roads crosses the entire country, serving growing settlements that require ever-increasing transportation. Rural roads. State highways. The local roads. City streets. These roads are built in several ways. Using natural gravel, crushed stone, concrete, and with the use of soil concrete. Ordinary soil reinforced with Portland cement for road surfaces exposed to heavy traffic is an effective and cost-effective solution to many of the problems faced by engineers in road design today. Soil concrete consists of soil making up at least 95% of the total mass and Portland cement. The amount of Portland cement depends on the design characteristics of the road section and the stabilizing additive used. Water. It is necessary for the hydration of the cement in the mixture, as well as to achieve maximum compaction of the soil. When mixed, the soil, cement and water form a dense paste-like mixture ready for laying the structural layer and its compaction. After that, the resulting mixture hardens, gains strength and does not come out of the mold, and it turns into soil concrete, which is resistant to moisture. In dry conditions, well-compacted soil can already be used as a road structure. However, moisture penetrates most soils, causing a loss of stability. Under the influence of loads, the road surface deforms and tends to break down. In other words, the soil becomes plastic and loses its strength. This problem can be solved by adding cement to the soil composition. It binds all the soil particles into a monolith, giving the material structural strength. Moisture penetration into the soil cement structural layer is minimal, and it retains its strength and stability under any conditions. Soil cement is a semi-rigid material having a high compressive strength limit. It can withstand significant axial loads without deformation. At the same time, having a high flexural strength, it resists dynamic loads from moving vehicles well. To determine the suitability of the soil for constructing the structural layer, samples are taken from the road's right-of-way at regular intervals along the road under construction. When using imported soil and a special soil quarry, it is also necessary to systematically analyze the samples. In the laboratory, the samples undergo several tests to select the soil concrete mix, determining the optimal amount of cement and water to obtain soil concrete with the required set of physical and mechanical properties. When selecting the soil concrete mix, the first step is to determine the maximum soil density at its optimal moisture content using the standard compaction method. For this, the soil sample prepared for testing is dried in a drying oven to an air-dry state. After drying the sample at a temperature not exceeding 100 degrees Celsius, the soil aggregates are crushed. Next, a soil sample of the specified mass is selected. The selected sample is placed in a metal testing cup. Cement is added based on the required strength characteristics of the soil concrete. The amount of water needed to moisten the selected sample to the moisture content of the first test is calculated. The calculated amount of water is added to the selected soil sample in several steps, mixing the soil with a metal spatula. To determine the maximum density and optimal moisture content of the soil, the test sample is loaded into a special mold in layers and compacted. After compaction, the collar is removed and the protruding part of the soil is trimmed flush with the edge of the mold. The cylindrical part of the mold with the compacted soil is weighed and the soil skeleton density is calculated. The compacted soil sample is removed from the cylindrical part of the mold and samples are taken from the middle part of the specimen to determine the soil moisture content. A graph is plotted showing the relationship between the dry soil density and moisture content. For cohesive soils, the maximum density value and the corresponding optimal moisture content are determined at the highest point of the graph. To determine the optimal dosages of stabilizer and cement, several mixtures of different compositions are prepared, varying the content of the added components. This is done with a specific increment. Samples in the form of cylinders are prepared from these mixtures by compaction. The compaction is carried out to achieve maximum density at the previously established optimal moisture content. The resulting samples are stored in airtight packaging for a period of 7 days. After the specified curing period, the samples are removed and their compressive strength is determined using a hydraulic press. The results of these tests determine the required cement content to achieve the specified strength parameters. In practice, the strength characteristics of soil cement are the basis for calculating the entire road pavement structure. At the same time, low soil strength may indicate the presence of various impurities in the original soil composition which hinder the hydration of cement. When stabilizing soils, it is necessary to study the initial physical and mechanical properties of the soil. The process begins with crushing the soil aggregates. First and foremost, the granulometric composition of the original soil is studied by analyzing the distribution of particles by size. To separate the soil into fractions using the sieve method, sieves with different mesh sizes are used. The residue on each sieve is weighed. The distribution of the finest soil particles is determined by the hydrometer method. For this, the residue is mixed with water using a high-speed mixer. Based on each measurement taken with the hydrometer, the total soil content must be calculated using a special formula. Then, the percentage content of each soil fraction should be determined by successively subtracting the smaller value from the larger one. The results of the analysis are recorded in a logbook, and a graph is also plotted showing the percentage distribution of particles across the sieves. The next important characteristic of soil is its plasticity. It is characterized by the plasticity number, which is the difference between the moisture content at the liquid limit and the moisture content at the plastic limit. For this, the soil is crushed and mixed with water to prepare a paste-like mixture. The soil moisture at the liquid limit corresponds to this specific moisture content. The soil paste at which the edges of the mass, placed 1 centimeter apart, come into contact with each other after 25 blows. This is determined by plotting a graph of the number of blows on a shaking table against the soil's moisture content. The moisture content at the plastic limit corresponds to the moisture at which the soil loses its plasticity and turns into a solid state. The moisture content at the plastic limit is determined by rolling the soil into a thread. Qualitatively, this corresponds to the state when a thread made from moist soil, as it dries while being rolled, begins to crumble into separate pieces about 1 centimeter long. Linear shrinkage is the third characteristic of soil. Soil shrinkage refers to its ability to decrease in volume as moisture evaporates from it. The soil is mixed with a certain amount of water, and the resulting mixture is placed into a special mold. Then the soil is dried to a constant mass, and the amount of shrinkage is determined. After determining the physical and mechanical characteristics of the original soil, it is necessary to assess the effect of various additives in cement on the properties of the stabilized soil. For this, the soil and a small amount of cement, possibly together with the stabilizer, are mixed, water is added, samples are molded, and they are left for 7 days. After that, the samples are broken up, crushed, and the changes are determined. The characteristics presented above are given for each soil composition containing different amounts of cement or additives. A small percentage of cement added to the original soil consistently improves its properties and allows for achieving the high performance required for constructing the structural layer of the road pavement. The results clearly demonstrate this. That for stabilized soil, the plastic limit increases while the plasticity index decreases as the amount of cement increases. Construction of a soil cement road begins with preparing a base of the required thickness and cross slope using either local or imported soil. Proper compaction of the base is an important technological step. The cement required for the road surface can be delivered by truck in bags. The bags are laid out along a specific path and then opened. Next, the cement is evenly spread over the entire area of the road section under construction for subsequent mixing with the soil. The spacing between the bags is calculated based on the required cement content and the thickness of the structural layer. Cement distribution can be carried out using a cement truck in combination with a mechanical spreader. The cement is fed from the cement truck into the spreading machine. As it moves along the roadbed, the cement spreader applies the cement in an even layer. Bags of cement can also be distributed mechanically using any other mechanism suitable for this purpose. Thus, spreading the cement significantly speeds up the process, minimizing the impact of bad weather. Mixing of cement, soil and water is carried out by machines that loosen, crush and blend the mixture. For example, a pH stabilizer. This is a special purpose machine that performs all these operations in a single pass. In the mixing chamber, all materials are thoroughly blended using a rotor equipped with a series of cutters. These cutters grind the contents into a uniform mixture. The required amount of water is supplied from a tanker moving ahead of the mixing unit. If necessary, a stabilizing additive is introduced, which can affect the water balance of the soil cement system. To achieve maximum density and therefore maximum strength, the soil cement must be compacted as soon as possible, right after mixing. The roller should follow immediately behind the mixing machine. Vibratory rollers have proven extremely effective for the initial compaction of certain types of soil. Pneumatic rollers are usually used for final compaction. During compaction, the surface of the structural layer is graded with a grader to avoid irregularities that could later cause various types of defects. At the same time, the root surface is also cleared of any foreign objects. The moisture content of the soil during the construction of the soil cement layer must be kept at the optimal proportion. It is also necessary to maintain the moisture of the laid layer until it is covered by the next layer. Watering after the stabilization process is essential to prevent the root surface from drying out. After this, the surface of the soil cement road pavement is finally profiled to eliminate minor irregularities. Then a layer of bitumen is applied, which is necessary to protect the soil cement structural layer and also to improve its performance characteristics. For most soil cement road pavements, the application of such an insulating layer is provided for the installation of a crushed stone surface. If heavy traffic is expected, an asphalt concrete mix may be applied as the top layer. In addition to the PH company's mixing machine, other stabilization equipment with a high-speed rotor is also used for loosening, crushing the soil and mixing. It mixes the soil with cement. Water for the mixture is supplied from a tank that moves ahead of the mixing machine. A road milling machine is another rotary machine designed for multiple passes over the road surface. Cross-mixing is necessary to eliminate unmixed areas and achieve complete uniformity of the constructed layer. During this operation, the moisture content of the mixture is maintained by distributing water from the tank. In this case, to prevent the formation of irregularities on the compacted surface, cultivation is carried out before the rollers pass. Equipment designed to carry out the entire stabilization process in a single pass is known as a stabilization train. It performs crushing, cement distribution, mixing of the soil-cement mixture, and compaction. The first unit of this mechanism is the cement spreader, which evenly distributes cement over the surface of the constructed layer with the required amount determined through laboratory tests, based on the example of the soil being used. At the output, the rotor loosens, crushes, and mixes the mixture. Water is supplied from a tanker moving ahead of it. The second unit of equipment carries out tamping and rolling of the pre-mixed mixture. Laboratory tests of the soil cement mixture must be carried out regularly to be fully confident in the achieved characteristics as well as the safety margin and durability of the constructed road structural layer. It must comply with all standards. The amount of cement can be determined by sampling. Samples are taken at the site of lean. Sampling of the mixture is carried out immediately after the passage of the mixing machine. They are used to determine the optimal amount of water in the mixture to ensure maximum density. Its quantity is determined using special equipment. The design strength of the soil cement is determined by studying the strength characteristics of soil samples molded from the laid mixture at the site and tested at the design age. The density of the compacted structural layer is determined by directly extracting a sample and sending it for analysis. The thickness of the structural layer is measured and the volume of the extracted material is determined by filling the hole with sand of known density. A sample taken from the fully completed soil cement structural layer obtained using a core sampler is examined to confirm that the soil cement mixture will gain strength over the years and that its safety margin will also increase. This will allow the road to maintain its load-bearing capacity even as traffic intensity continues to rise. The flexural strength limit of the soil cement roadbed is determined by on-site testing using a long base lever deflectometer with the static loading method. The process of soil stabilization using Portland cement has proven itself in a wide variety of projects over the course of a quarter of a century. The technical stages of the equipment have been improved to such a level that it is now possible to create a high-quality structural layer while saving money on its construction. Wherever roads are needed for transporting goods, for urban traffic, or for agricultural purposes, soil cement pavement is a progressive material in the field of road construction. In all regions of the country, soil cement can provide the creation of a reliable and long-lasting transport infrastructure necessary for regular road traffic. The construction of economically advantageous first-class roads which require minimal subsequent maintenance contributes not only to present prosperity but also to the future development of the entire national road network.